Right, this is Chapter 11, Lesson 1, Part B. So we're going to be covering permutations with repetitions, and then later on permutations with constraints. So first of all, what do we mean by permutations with repetitions? Well, here's an example. Imagine that the letters of the word book are written on tiles. So on one tile there's a B, and then there's an O, and then there's another O. We want to rearrange the tiles. How many different arrangements are possible? Well, for now, what I'm going to do to make sure that we recognize the difference between the two O's, how about when I write it, I'll write one of the O's in blue and one of the O's in green, just to keep track of it. So if I start off and I write here B O, and then I'll put a green O, and then back to my blue K. So that would be my first one, right? So another way I could write it is if I pick these tiles, the two O's in the different order. So if I wrote B and then OK here, and then the green one there. Okay, so how else could I rearrange this? If I'm going to do all the ones that start with the letter B first. So now I'll go B, I'll go blue here, and I'll go, how about if I switch these ones here, and I go with the K, and then the other green one. So and then I'll switch the O's again. So I'll get okay, so I'm gonna pause and then just write them all out because I think it'd get kind of boring just to watch me because there's quite a few. So I'll do that and I'll be right back. Okay, now I've written them all out. Oh, I noticed I didn't fill in quite all of my missing O's here. So you see, I tried to do some type of a pattern so I just wouldn't miss any. And don't worry, this isn't something that you're going to be having to do. I think it's just to illustrate our point. And here's the point. You'll notice that here's book and then book. The two O's I switch, right? Because these are physically different tiles. And now I wrote one blue and one green just so that to remind ourselves that these are two distinct different tiles. But when we make the arrangements, these O's wouldn't be the same color or wouldn't be a different color, and these would look identical, right? These two would look like the same one. So let's read what the text says. Now that we've written them all out, we should notice that many of the arrangements are identical. For instance, Kobo and Kobo, so that's right here, look the same, but I've switched the O's. So although we have 4 factorial, and that's going to be the same thing as 4 times 3 times 2 times 1, which is equal to 24. And indeed, if I do count these, 2, 4, 6, 12, 24, there are 24 there. So although there are 24, the fact that each one is represented twice here, we really can divide by 2. So how many would this be? 4 factorial divided by, and you'll see the reason why I'm going to do 2 factorial instead of 2, even though 2 factorial, 2 times 1, is the same thing as 2. We really only have 12 different distinct ones. So if the question was, how many different arrangements can you have of the letters B, O, O, K, you'd say, all right, there are 4 letters, therefore 4 factorial, but one of the letters repeats twice, so I would divide by 2 factorial. This 2 because there are 2 O's. All right, so here's our general rule. In general, a set of n objects with a objects that are identical can be arranged n factorial divided by a factorial. What happens if there's more than one set of repeats? So if looking down really quickly, here's an example where I've got an 8 repeating and a 1 repeating. Well, we can make more of them. We can say n factorial divided by a factorial, b factorial, c factorial. So may not make too much sense now, but when we do a few examples, I think it'll make more sense. All right. Again, how about I'll do the your turn, you don't fill it in, you hit pause and then do it yourself. And you probably by memory because it's really not that complicated. So in how many different arrangements can you make using all the letters in Manitoba? Well, first thing we need to do is we have to figure out our number of letters. So if I count 1, 2, 3, 4, 5, 6, 7, 8. So in other words, my n is going to be equal to 8. I have 8 letters. So I know that the numerator is going to be 8 factorial. Now, are there some repetitions? It seems to me when I'm looking at it, my A That's the only thing that's repeating, and there are two a's. So I'm going to be dividing by 2 factorial. So 8 factorial, so I'll say 8 letters, 2 a's. So 8 factorial divided by 2 factorial. I'm not even sure what that is. Let's just check it out. Okay, I just used my calculator, and it is 20,160. How many different arrangements of all the numbers of 81818 can you make? Okay, so let's count the letters. There are 1, 2, 3, 4, 5 letters. So in other words, I will have 5 factorial. Now I'm going to have 2 factorials in the denominator because it seems to me that there are 3 8s and there are 2 1s. So in other words, A is going to be equal to 3 and B is going to be equal to 2. So I will say 3 factorial times 2 factorial. You don't even have to have a multiplication symbol in between there. So what is 5 factorial divided by 3 factorial, 2 factorial? That works out to 10. So there are, that's not a 16, it's a 10. Make that better. There we go, 10. I'll even put a box around it, make it special. Okay. Here's a neat one. How many paths can you follow from A to B if you can only move up or left? So it's like if you're going from, school to home and you've got these number of blocks to do, how many different ways can you do it? Well, if you have to move only up or right, okay, let's think about this. I'm starting here. At some point in time, I have to go up, up, up 3 times, right? So in other words, I've got one way to do it is to say up, up, up. 1, 2, 3 times. I have to go right 1, 2, 3, 4, 5 times. 1, 2, 3, 4. There we go. So this would be maybe the code for if I was taking that path. That would be up, 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 right, 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 right. I can do any variation on this, right? I can go maybe up, up, right, and then right, 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 up. I'm just switching one of them here. So if I was to do that way, it would be up, up, and then a bunch of rights, and then up. Okay, so I just, oops, somehow it all erased there. So the second one is like that. Okay. What my point is that we can change this question into a question about arranging letters of a word. So thinking about, I've got these letters, how many different arrangements can I make of that, of those letters? Well, I have 1, 2, 3, 4, 5, 6, 7, 8 letters altogether. So I'm going to get an 8 factorial over, well, I've got 3 U's, and I have 1, 2, 3, 4, 5 R's. So that's how it works out. So 8 factorial divided by 3 factorial, 5 factorial. I think when I do the math, I get 56. Here's a little note about Kobo. Did you notice that Kobo is actually just a permutation of book? Oh, those guys. Okay, now permutations with constraints. And if you want to, you can take a look, and the textbook has the same example on page 522, example number 4, and they do a bit more extended of an explanation. So here we have 5 people seated on a bench. In how many different ways can they be arranged? So before we go on this constraint, let's just think about, okay, if we got 5 people on a bench, so we have 1, 2, 3, 4, 5 spots, and let's say that there were no constraints. Let's pretend right now, in how many ways can they be arranged, and forget about the if part, okay? Well, we would put, the first person, there's 5 different ways because there's, 5 people, so we can put 5 people there, and then we could put 4, and then we could put 3, 2, and then there's only 1 left, we have to put that person there. So it's another way of writing it very quickly is to say 5 factorial. Like, so as soon as you have some number of people to seat in a row, it's always going to be that number factorial. Okay, so with that started, now let's think about this first constraint. It says, what if E has to be seated in the middle? Okay, so if we're doing this question, there's my 5 spots. Now this one has to be the letter E. So there's only one way to do that. Okay, now at this point, there are 4 people left, right? There's 4 places for them to go, and there's 4 people left, so it's going to be, there's 4 different ways to put that one in, 3 different ways to put this one in. Now there's only 2 people left. There's only 2 ways to seat someone in that chair or in that place in the bench, and then there's only 1 person left. So really, when you look at this, this would be, you place your first person down. Okay, so whenever you have these constraints, deal with the constraint first. Okay, deal with the restriction. Another word we use. So put this person down first, and then put the rest of the people down. So really, this is going to be the same thing as a 4 factorial. Okay, which I think is 24. Okay, so for the next one it says, what if A and B must sit together? Okay. Oh, A and B, they're such troublemakers, making and saying, oh, we have to sit together. All right, so here's what we're going to do. We're going to go and we're going to pretend that A and B are 1 person. Okay, so the words we often use for this one is that we're going to, it sounds a little bit mean, but we are going to tie A and B together. Okay, so what that means is we're going to think of them, pretend that they are 1 object. Okay, AB is 1 object. So now how many objects do we have? Well, we have AB, remember they're tied together, and then we have C, D, and E. So we only have 4 objects to place, right? These guys are going to take a double spot, but that's okay. So now we have 4 different ways to place: A, B, C, D, and E. So when we place these, this is going to be equal to be 4 factorial. Okay, but we're not quite done, because now we have to think about how many different ways can we place AB, right? In each of those situations, let's say if we put AB here, right, and then we put C and D and E there. That would be one of the ways in this 4 factorial, in this 24 different ways. But we could also say it would be identical if we did BA, right? So within this group of AB tied together, there are, since there's 2 objects, right, we have to place them within these 2, A and B. There's going to be 2 ways to put down A or B in the first spot, and 1 way to put them in the second spot. So there will be 2 factorial. So just thinking about this, we're kind of doing two decision making. One is seat the group of 4, okay, and that's 4 factorial. And now within this group of 2 that we made, we have to seat them, okay. So since we have to do seat the group of 4 and the group of 2, when you see the word and, we're going to be multiplying. So it's going to be 4 factorial multiplied by 2 factorial. First we did this and then we did that. It's kind of like your salad and then your entree. So it's 4 factorial times 2 factorial, which is equal to 24 times 2, I guess that's 48 different ways. Okay. What about if A and B must not sit together? Okay. Well, if you wanted to refer to the textbook, if you wanted to go back, they have kind of a long version and then a short version. And I think I'm just going to teach you the short version because I like it so much better. When you see these not type of a questions, right? How many different ways can A and B, or can they sit if A and B must not sit together? Really what we're going to do is we're going to say, what are all the ways minus if A and B must sit together. So if we think of the entire different set of how A, B, C, D, and E, thinking of them of 5 different ways, 5 different people sitting down, all the ways they can do it is 5 factorial, right? And that's pretty straightforward, no restrictions at all. But then if we take away where A and B are sitting together, and that's what we just did, well, tie them together, put the 4 together, and then within the group of 2, seat those ones. This will be our answer. So 5 factorial is 120 minus, we just figured out that was 48, so we would get 72 as our answer. Okay, let's do the your turn, and again, I'll do it once. Alright, here we are looking at the your turn. So I'm doing this for the second time because I made a bit of an error on it before. So hopefully it'll go better this time. So first of all, we need to take a look at the question. We have to arrange 3 different calculus books, 5 different biology books, and 4 different economics books on a shelf. How many ways can you arrange the books if not restricted? So it's just a normal put the books on a shelf. And by the way, the calculus books are all different, so it's not like they're identical. All these things are different, so they're not identical. So it's not an example of trying to build a word with 3 C's and 5 B's and 4 E's. Rather, I just have a bunch of books. How many books do I have? 3 plus 5 plus 4. I've got 12 books. So I'm just arranging 12 books. So the number of ways that I can do that is going to be equal to 12 factorial. And when I plug that in, my 12 factorial is a really large number, 479001600. Put some commas in there. 47 million different ways. Oh, no. 479 million different ways. That's just crazy. Okay, so there's lots of different ways to do that. And the next question is, now, how many ways can you arrange the books if they must be arranged by subject area? So, in other words, I need to put all the calculus books together, all the biology books together, and all the economic books together. So it's kind of like in our previous question where I had A and B must sit together. Here it's all the calculus books must sit together, all the biology books must sit together, and all the economic books sit together. So the first thing we're going to do is like sort of step one. We're going to tie together the subject areas. So tie together the books by subject. At this point, after we've tied them together, I have one object, which are the calculus books. I have a second object, which is the biology books, and I have a third object, which is the economic books. So when we place those, so we have 3 objects, and we need to place those, and so that will be 3 factorial. Or 6. Okay. Now our second step. Now within each one, within each one, calculus books. So place objects within each group, each subject group. So looking at the 3 calculus books, how many different ways are there to place the 3 calculus books? 3 factorial. How many different ways to place the 5 biology books? 5 factorial. How many different ways to place the 4 economic books? 4 factorial. So at the end of the day then, once we've done both steps, it will be 3 factorial times 3 factorial times 5 factorial times 4 factorial. This 3 factorial represents the placing of the 3 subject areas. Now within the first subject area, this is placing the calculus books, the biology books, and then the economic books. And when we multiply all that out, we get a fairly large number. Not surprising, 103,680. Okay, so that's the answer for our second question. Now our last one, how many ways can you arrange the books if all the calculus books must go on the right end of the shelf? Okay, so let's imagine we have 12 books altogether, right? We added those together. We had 12 books. So if I made 12 spots here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These last 3 will be where the calculus books have to go. Right? So placing those calculus books on the last 3 first, it will be 3 ways to put the first one, and then 2, and then 1. Or another way to say this is 3 factorial. Now this would be all other books. And there are no restrictions on this one. And there are 9 of them. So that would be, I could write 9, 8, 7, 6, but it's 9 factorial. So my answer is going to be 9 factorial times 3 factorial. Which gives me, could it be, oh, hold on a second. I had to grab my calculator because I cannot do that in my head. It is 2177280. All right, there you go.